So before we've looked at the standard normal curve, which was a z distribution, so we can call it, and then we've looked at just normal distributions. Now what we have is something called a student t-distribution. I know it's a strange name for it. There's kind of an interesting story in the book that goes through where the name came from. I think it's really interesting. I think you guys should read that. But so a little bit about the student t-distribution. We have a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, then the distribution of t equals x bar minus mu divided by s, which is our sample standard deviation, divided by the square root of n, follows student's t-distribution with n minus 1 degrees of freedom, where x bar is the sample mean and s is the sample standard deviation. So this kind of looks like our sampling distribution, but we're dealing with the sample standard deviation instead of the population standard deviation. So the reason for this is a lot of times we don't know the population standard deviation, but we do know the sample standard deviation. So here, what do we mean by degrees of freedom? So if we're picking certain items out, then say we have 5 items and we can pick them in any order we want. Well, the first 4 items, we have a choice of what way we want to pick them, but the last item, we have to pick that item. There's no other way that we can pick it. It has to come in a certain order. So the reason we pick the n minus 1 is so that those items are in that order, and so that it falls, and so that everything falls in line. So we're going to kind of use that to go along with that, and we're going to be using t interval instead of z interval, and that's because a lot of times we don't know the population standard deviation. So let's look at some properties of the t-distribution. So kind of comparing the two of them, they're both symmetric, they're both centered to 0. With z, the rectangles are mainly between, -3 and 3. The histogram for t is more dispersed, and that's due to the fact that we're using the sample standard deviation, which is random, whereas the population standard deviation is constant. And z follows the standard normal distribution, but it's unlikely there that t follows a standard normal distribution. So looking at some properties here, the t-distribution is different for different degrees of freedom. It is centered at 0 and symmetric, about 0. The area under the curve is still 1. The area under the curve to the right of 0 equals a half, and the area to the left of 0 equals a half. So this is all kind of the same as what we had for the standard normal curve. As t increases or decreases without bound, it approaches but never equals 0, same as before. The area and the tails of the t-distribution are a little bit greater than the area and the tails of the standard normal distribution because we're using the sample standard deviation as an estimate of the population standard deviation, which is introducing further variability into our t-statistic. So as the sample size increases, the density curve of t gets closer to the standard normal density curve. So again, we're using this, or the idea of law of large numbers comes in. So you can see here we have 3 curves. So we have the normal curve and then a t-distribution where the sample size is 15 and 5. So you can see when the sample size is 15, it's closer to the normal distribution, and when it's 5, it's not as close. So you can see with that sample size increasing, it becomes closer to the standard normal distribution. So like before, we were working with z sub alpha over 2, z sub alpha. We can do the same thing and look at t values. So we have a separate table for those because it's dependent upon our degrees of freedom. It's just dependent upon our sample size. So I pasted over the table. There's a Word document or a PDF posted in Moodle with those values for you. I've just pasted what we needed here. So first thing we do is find the t-value such that the area in the right tail is 0.005 with 5 degrees of freedom. So here we want to be careful. The z-score table with the standard normal curve dealt with the area under the curve to the left. This one deals with to the right. So we have the area in the right tail is 0.005. Have that there. And then 5 degrees of freedom. So I'm going to find that here. And then I just draw the line, match those up here. And then I'll have to value where those two overlap. So here we're looking at 4.032, and that would be my value there. So the next one, we want the t-value such that the area in the right tail is 0.01 with 16 degrees of freedom. So same idea. So 0.01. Oops, I don't want to use that color. So 0.01, and then 16 degrees of freedom. So here we're looking at 2.583. Okay. So next one, the area in the left there is 0.15 with 17 degrees of freedom. So we can still use our table. So 15, so we're just gonna that, and then 17 degrees of freedom. So the one for right is 1.069. We use symmetry. So our left one is just going to be the negative value there, right? Lastly, we want to find the critical t-value that corresponds to 96% confidence. So again, let's start. Apologize for that. My dogs are kind of running around rampant in the house. But, okay. So 96% confidence here. So let's start off by drawing our bell curve. So we have that here, 96 in the middle. So I split that, so 1 minus 0.96 divided by 2. Each side in the tail is 0.02. So that's the area in the right would be 0.02. And then our 8 degrees of freedom. So if we map that down, so 0.02, 8 degrees of freedom, we end up here with 2.449 as our critical value there.